Okay, so here we talk about the ammeter and voltmeter. So I suppose you already know something about that. But anyway, here we slightly talk about what's the difference between ammeter and voltmeter. So for ammeter, it is used for measuring the current, and for voltmeter is used for measuring voltage. And of course, there will be some characteristic difference between them. Okay, for ammeter, when we try to measure the current, for example, I here, we will try to connect this ammeter in series. Okay, so in that case, so originally the circuit should look like this is R, this is the battery E, and then this is R2, this is R. This is R2, this is R1. The original circuit should look like this, okay? Before we plug in any ammeter or voltmeter. This is our original circuit. Okay, so here we try to measure the current I. So we try to connect this ammeter in series with this loop, which means that we can connect the ammeter here to here. Or maybe we can just put it here or here. It is still fine. Okay, because the whole loop should have a current I. So maybe we can just put it here. And of course, for the characteristic of the ammeter, it has a very small intrinsic resistance. It should have a very small intrinsic resistance. So here we talk about, we use the ammeter to measure the current I. It is essential that resistance RA means the intrinsic resistor of the ammeter. This is the intrinsic resistance, should be very much smaller than other resistance. Because if you connect the ammeter here, it feels like it has an intrinsic resistance RA in series with a circuit. If RA is comparable with this resistance, you can see this resistor are in series. Okay, so the total resistance will be like R total. R total will be RA and then plus R plus R2 plus R1. Okay, originally the resistance only have a small R, R2, R1. Here, if you connect the ammeter, it becomes these terms plus RA. So if RA is comparable with them, we will change the R total. If RA is much smaller than the others, then whether you connect the ammeter there, then total resistance will be the same. And this, so if R total doesn't change, R wouldn't change. If RA is large, just say if RA is equal to R, then it will change the current. So it doesn't make sense because you want to measure the current without this one. So after you connect it here, even though RA is not 0, but you hope this is small enough so that it won't change the condition of the circuit. So that's why RA should be small. RA should be much smaller than RA or RB, R1, R2 should be much smaller than the others. Okay, and for the voltmeter, it used to measure the voltage. Just say you try to measure the voltage across R1. So to find the potential difference between any 2 points, the voltmeter are connect to those points in parallel. Okay, and then you will hope this RV should be large. Okay, here it says, okay, so for voltmeter, try to measure the voltage across R1. It is essential that the resistance RV of the voltmeter should be much smaller than the resistance of any circuit of the element. Because here, you will have a resistance. Just say you connect the voltmeter here, CD. So here, this is C, this is D, which means that you connect RV here. Okay, so R1 and RV are in parallel. So which means that originally R total equals R plus R1 plus R2. So after you connect RV there, it becomes R1 parallel with RV. Of course, this parallel operation calculate first. So in this case, the parallel resistance is like R1 times RV over R1 plus RV. So here you will hope that RV is much larger than R1 and R2, so that this parallel operation doesn't change the value. If RV tends to infinity, so RV will be much larger than R1. Okay, so for the denominator, it is nothing but RV, and RV will cancel. So it shrink back to R1. So if RV is very large, it doesn't change the R total, and in that case, it doesn't change the current or other voltage at the nodes. So in short, for ammeter, we hope the intrinsic resistance RA to be smaller than the other. And for voltmeter, we hope the intrinsic resistance of a voltmeter much larger than the other resistance. Okay, so next we talk about the RC circuit. So previously we have talked about the RL circuit. So yeah, this is the other one. So for RC circuit, we should have an equation like this. It is quite similar to what we get for the RL circuit. For the RL circuit, there are some different. The tau L will be something like L over R, but here we have tau equals RC. But generally, the expression are so alike. So let's see how we can derive it. Okay, so here, suppose we have a battery. Let's call it E, and then we have a switch there, and then we have R and C in series. And then so let's suppose this is the ground. Okay, so this is plus minus. And then at t equals 0, the switch will be closed, so that there will be current there. And here we will assume that V0. Let's say this is V. This voltage across the capacitor is V. So we will expect V0 negative is 0 volt. This is the initial condition. And if you still remember, the voltage for capacitor is continuous. So we will have, so as much as this is continuous, so we should have V0 plus is also 0 volt. Okay, so and also for capacitor, we also expect the current is I, because it's single loop, we only need to assume a single current. Okay, so for the current, I will be C dV C dt, C dV dt. Or maybe you can call it VC, if you like. So maybe you can call it VC. Here, VC. So maybe let's call it VC rather than V. So this is VC, C dV C dt. Okay, so here we try to write the KVL. We start from this point and then go for a loop. Okay, so this is going up, so we have E. And then here we're going down, I times R. R times I plus VC. VC is from plus to minus. So this is VC, so VC. So in that case, we have I equals C dV C dt. So we can just put this one to here. So we have R times C times dV C dt plus VC equals E. Okay, so let's try to normalize it, because we usually want the leading coefficient to be 1. So we have a dvc dt plus 1 over rc times vc, which means that we divide both sides by rc. Okay, so it becomes something like this. Okay, so this is a constant coefficient ODE. So the first thing is to solve for the homogeneous equation, which means that we let the right hand side to be 0. So in that sense, if we try to solve for the homogeneous equation, we try to change this to be s, because this is the first derivative, we change it to s, and then plus 1 over rc, and then equals 0. Now this is the original function, so you change it to 1. So we have s equals negative 1 over rc, which means that Vc, the complementary or the homogeneous solution, is a times exponential to negative t over rc. Okay, as much as we have this one. Okay, so this is a constant. This is a constant. So we will expect Vcp is also a constant b. It's a constant b. Okay, this is a particular solution. And then we can just plug in this one to here. Okay, so for the first derivative, the constant will be 0. And then for this one, we have a 1 over rc times b equals e over rc. So we can quickly get that b is negative, b is e. B is e. Okay, so Vc of t should be Vcc plus Vcp. So it is nothing but b plus a exponential to negative t over rc. And then as much as we get the initial condition, which means that we know Vc of 0 plus is this is e. This is e because we already know this is e. So it is e plus a. When we plug in t equals 0, exponential to 0 is 1. So we have e plus a equals 0, 0, 0. Okay, so we get a equals negative e, and then we can get Vc to be e times 1 minus exponential to negative t over rc. Of course, we can just let tau c to be rc. Then we can write it as Vc equals e times 1 minus exponential to negative t over tau, like this. So this is actually the same as this one if we assume tau to be rc. And for the I is straightforward. I is nothing but c dvc dt. Okay, so that we can just plug in this one to here. So we will get c times dvc dt. So this is e. So we have e here, and then we have, this is a constant. So take the derivative will be nothing but 0. And then also here we have negative sign, and then negative sign, and then exponential to negative t over tau. And then for the derivative, we should have the chain rule. So it multiplied by negative 1 over tau, which is plus 1 over tau is rc. So we have rc here. And then finally, we can just cancel this c and c. So we end up have a e over r, and then exponential to minus t over tau, which is actually this one. So we need to know how to solve the constant coefficient ODE to really get this expression. Okay, so and of course here it is another condition, like, so here after charging the capacitor for a long time, then we will assume that for this case V0 minus is E. which is charged by this battery. And then at t equals 0, the switch go from A to B, so that the charge on the capacitor will be discharged to the ground. Okay, so this is the other situation. So in that case, the current circuit will look like this. This is C, this is VC, and then this is I. Okay, so writing the ODE governing this circuit will be like R times I plus VC equals 0. Here we only have 0 because here we just switch this node to point B so that we disconnect the battery, and then we try to connect it to ground. So we don't have the battery here now. Okay, so in that case also we have I equals C dVC dt. And then we can just plug it here. So we have RC dVC dt plus VC equals 0. And then we will have a dVC dt plus 1 over RC VC equals 0. So we have 0 on the right side, so we don't have particular solution, which means that VC is actually the same as the before, which is A times exponential to negative T over RC. Okay, we don't need to add B because we don't have the function on the right side. Okay, so in that case, we know VC0 plus should be E. Okay, so let's plug in VC0 plus is A, because we plug in 0, this is 1, and then is equal to E. So finally we get VC equals E times exponential to negative T over RC. So which is actually the same as this one, or maybe you can just call it V0 rather than E. And of course you can just use I equals C dVC dt, and then you plug in this one to here, then you will get this expression. Okay, so this is called an exponentially decay. So this VC start from V0 and then finally will be 0. Okay, so this is V0, this is VC, this is T. Okay, so I think, yeah. Okay, so this concludes this